Alright, so today I wanted to start talking about logarithms, natural logarithms, and exponential functions. Once I start the calculus series, you'll understand why I added the exponential functions to the same video as logarithms and natural logarithms, but for now I'm just going to tell you what they are and how they work. So when it comes to logarithms, they always are composed of these things. It's a base, we'll just call it b, and then some number x, and it's equal to y. So now we know what it looks like, but how do you put it into terms that are different than this? Because, here, how do I explain this? You know PEMDAS. There's exponents, multiplication, division, subtraction, and addition. Subtraction undoes addition. Multiplication undoes division. So think of logarithms as undoing exponents. Alright, so when you're doing a logarithm, it'll end up in the form of b to the y equals x. Oh, I should probably lower that. I don't want to confuse you guys. Okay. So, the thing is that these bases, you can always assume that they're 10 each time. Unless you want to use Euler's constant, which ends up a natural logarithm, or just 2. If you're given a problem and it specifies which base it is, then you use that base. But if it doesn't give you a base, always assume that b equals 10. See, when the Babylonians actually found the logarithm first, and the reason why we have the degree system the way it is today is because they were using base 60. And that's how it led up all the way over here. So, now let's start talking about the properties. Here. Okay. So when you have this number, here, I'm going to remove the b, but always remember, the b will always be 10 if I don't specify. So you have it log x to, let's say, w, and w being any real number. If you remember this notation, this is w is an element of real numbers. When that happens, this is the equivalent to w times log x. That's a property. Alright, so the next property. If you don't mind, I'm going to erase w as an element of real numbers. Okay, now, the next property is going to be one that's adding logarithms. So, let's just say, let's call this log x again, plus log, z. This is the equivalent to log x z. That was a stupid z, but when you add them, it actually multiplies this part, these parts together. And that's another property. The next one is going to be subtracting logarithms. When you subtract them, it actually divides these two parts. So it's going to be log parentheses x divided by z. Alright. Now here's our final property. It's going to be dividing logarithms. Here, let me just check if... Alright, I just didn't want it to be blurry. See, this one actually has a pretty cool property, because when you divide logarithms, it actually replaces the base with the denominator, whatever was in the denominator for the logarithm, and then it's just x. these are all the properties that you will need to know once you start doing calculus. Now let's start talking about natural logarithms. Okay. Alright, so the thing about natural logarithms revolves around this transcendental number, which is about on the level of pi, and it was discovered by this guy named Euler. You can pronounce it Euler, but that would make you not German, which I'm not sure if you are. It doesn't really matter to me. But it's going to be this. Right there, that's going to be the base of this next logarithm that I'm going to be talking about. So, ln, you always know that it's going to be e whenever you see ln. That just means natural logarithm. And, oh wait, I should probably tell you guys this. Think of this as like an identity. So if log b to some base is going to be, it's always going to be 1. That's another property you should know. Because once you figure that out, as like once you start graphing functions of this, you'll be able to figure out what the function is based on, well, this single property, which is actually really important. So that's why I called it an identity. But anyway, so natural logarithms are no different from regular logarithms, other than that they have this really special constant that's involved with like Euler's identity formula, which involves e to the I pi equals negative 1? Something like that. Which is, it has a huge application in physics that I want to talk about in some other videos once I get through this series. But for now, let's just continue on with this. Okay, so now let's talk about the domains of these logarithms and natural logarithms. Here, let's put this into, let's see. Let's just make this into a function real quick. So, have you ever seen an exponent? Here, I'll put it into a form that you all can think about. Make this a negative number. Just the x. Will there be any negative number that you can actually use to get here, e to the y? What y value can you actually get a negative number? Simply, actually, when will e to whatever number get to 0? It won't. I'm going to give an explanation right now on why, because they explained it this way. So, let's see, I'm trying to remember what I was going to say. So, if you have e to the 1, that equals e. But e to the 0 equals 1. How would that be? Well, if e to the 0 equaled 0, then the rest of this would have to collapse with it, not even being a function. I mean, we could say that any single function such as that would exist, which is why we actually have to have e to the 0 end up not actually being 0. And e to the negative number, think of that as inverse, meaning that it will just get smaller and smaller, but it can't reach 0 unless you define it to be a negative number, which it still won't make sense, because how would you reach it to a positive number? And that's the reasoning behind that. There would be a proof. I might link it to the bottom of the video description, just in case if you want to read it. I could go look for it. I read it somewhere. But anyway. So now let's start talking about the logarithmic graphs. By the way, the natural logarithm will have similar graphs to the logarithm, but you can apply natural logarithms to a wide variety of things, like population growth and stuff. Actually, that's just Euler's constant in itself. that's always going to be related with growth. But we'll talk about that once we get to those types of videos and differential equations. So, when you see... Okay. Let's see. So I completely blanked out. I was trying to think of something else. But anyway, these graphs will always look like this. And the thing is that this kind of resembles that of a fractional graph. You know, where it starts colliding at over here, infinitely approaching it, as we talked about limits before, but they aren't very much like fractional graphs. Like I remember reading about this thing Littlewood did, where he proved that at some point it will go back to being negative, like, I don't know, somewhere out in infinity. Well, anyway, so I think that was by analytic continuation. Now, I'm a little fried right now, so bear with me. But now we're going to start talking about exponential graphs, or exponential functions. Okay, so an exponential function will have this form. Now you'd think, wait a minute, didn't we just see this? Alright, well, let's just put into a form that you should know as we've been talking about it. Log W y equals x. Now that's strange. So this is still a logarithm. What can this tell about the graph? Well, we defined it to have no negative numbers. We defined it to have no number that can be 0. So that means it will be a positive infinity, all positive real numbers. So that means the graph will look something like this. See? This stuff I didn't think was too hard. Sometimes you'll have to apply it to like population growth and stuff, and we'll push more on that in differential equations or calculus in general, because there are going to be a lot of applications throughout calculus. I think what was it? Related rates is going to tackle you if you go to college or take that AP calculus. But I think that's it. I think that's all I have to say. Thank you for watching. I'm not sure if I seemed as enthusiastic right now. I'm kind of out of it. But in the next video, I'm going to start talking about manipulating functions. I didn't really know how to like state it as a video title. I just called it that. I feel like there's some mathematical term in changing functions, like stretching and compressing. But yeah, that's pretty much it. Thank you for watching. God bless you. See you in the next video.